The last notion I want to talk about in terms of hashing, and I will talk about it very, very briefly, is the notion of uniform hashing. Sorry, not uniform hashing, it's open addressing. Open addressing. Okay. So what is the idea of open addressing? It's very simple. So far, the way we have been looking at the hash tables is that we have the table itself and we have the M slots in it. And once you map elements to it, you can have a linked list, for example, here, of all the elements that map to that. Okay, so this is by we're dealing with collision, resolving collision by chaining. Okay, in open addressing, so if you look at this, for example, at this table here, so we have m spaces in the array itself for the table, and then we have all the space for the linked list. But imagine now we don't want to allow linked list and all the elements go into the slots in the array itself. So now we can think about it as a much taller. We still have from 0 to m minus 1, but now think about m as much larger, but we will not allow a linked list. So whenever you want to hash an element here to the table, you put the elements in the table itself, not as in linked lists, and we will not have any of these. We will not allow chaining in the case of collisions. Okay, so here when I am mapping, so if I have the universal set of keys, and I have this set of keys here, and I want to map them, so I map the first one. Suppose it goes here, and suppose I map the second one. Suppose it goes here. If I map the third one, and suppose the third one is going to come to the same place where the second element was mapped, I will now say, okay, that place is occupied. I need to compute for it as another place. So now I compute another place. For example, it comes here. Okay, and the same thing with the fourth one. So if I'm trying to map the fourth key, I compute h of k. If h of k is occupied, I say, okay, it's occupied. Let me compute another h of k. If the second h of k is occupied, I'll say, let me compute another h of k, and so on. So now our hash functions become, we need to index them by the number of times we have been trying, or what attempt of hashing the element we are looking at. So remember that originally, let me say here, original or standard or not open addressing, this h was from u to 0 to m minus 1, right? We mapped every key to a slot there. Now, what we are going to do is that we have u, but in addition, we are going to also index the time we are doing the hashing. So now, if you look at this function, the input is a pair, a key, and some index for it between 0 and m minus 1. So now we can think about h of k0, h of k1, h of k2, and in the worst case, we have h of k m minus 1. So what does h of k0 mean? H of k0 is that first compute h of k and look at the table. So suppose h of k is 2, then we look at entry 2 in the table. If it's not occupied, we are done. We don't have to compute any more h of k. If it is occupied, now we go to h of k comma 1. This is now the second attempt in trying to find a slot for k in the table. If this fails, we go to h of k comma 2. Okay. In the worst case, we keep trying and we go all the way to h of k m minus 1, and we failed, then this means that the table is full. Okay, so this sequence here of this sequence that I just drew here, h of k0, comma h of k1, h of k2, h of k, and so on, this is known as the probe sequence for key k. Okay, so this is the probe sequence. Okay, so this is basically how open addressing works. We say we want to if we want to hash an element there, we look at h of k. If it is if it's occupied and that's not what we are looking for, we go to the second one and so on. So now we need to think about insertion, insert, and search, and delete. So how do we insert into a hash table under open addressing? So imagine that you have this table. We have this table here, and I have key k, and I want to map it. Suppose I want to, so I compute h of k 0, and suppose it's this one, but it is occupied. I said, okay, I cannot put it there. I compute then h of k1. Suppose I come here, it is occupied. I say I cannot do that. I compute h of k3. Now I come this way here and it's not occupied, so I insert here, okay? Now, again, insert is going to have a simple loop for I equals 0 to m minus 1. And we compute h of k0, h of k1, h of k2 until we get to a slot that's empty. Then we insert k there. If we have gone through h of k0, k1, k2, all the way to km minus 1, and we couldn't find any place, then we have the table is full, and we just return that the hash table is basically full. The same thing with the search. If we are searching for key k, then I can go to this table here, and I'm looking for key k. So I compute h of k0, and I look for the place in the table. If that's the key that I'm looking for, then I'm done. If it's not, I compute h of k comma 1. I come to the second place. If it is I'm looking for, then I return h of k. Otherwise, I go to h of k comma 3 and so on. If we tried all the way to h of k comma m minus 1 and we couldn't find it, we say we are done. It's not in the table. Okay. Deletion, we have to be careful about it a little bit, because think about what happened during insertion. So suppose I wanted to insert key, the key k equal 5, and suppose I looked at position. So suppose h of k0 was 2, h of k1 was, let's say, 5, and h of k2 was 9, h of k3 was 11, and this is where we stopped. So key 5 was inserted into position 11. So if this is position 11 here, this is where the key was, okay? Because 9 we failed, we couldn't put it there, and 5 we failed, we couldn't put it there, and 2 we couldn't. Now imagine after we did this, we had done delete, for example, 5, okay? So delete the key at position 5, okay, at this place here. So if we delete this, and we come next to search for key k equal 5, then we're going to come to 2 here. We say it's not there. Then we are going to go to h of k1. We're going to come to this entry here. We find it is empty because we had done deletion on that. Then we will be under the impression that, okay, the key is not there because we have h of k1 is empty, and if k was there, it should have been put in that empty slot. But this is just an artifact that we inserted k equal 5, then we deleted one entry that was probed on the way to finding the best position for k equal 5. And when we are doing the search, we hit an empty slot, and then we say it's not there. This is an easy solution for this is just to put a flag there in that entry there. When we delete, we put a flag to denote that there was an element and this element was deleted. So we distinguish between two types of blank entries in the table. One blank entry is an entry that nothing has been mapped to it. So it's completely blank and everything is fine, that in the sense that if we want to insert, we can insert there. And when we are searching and we get to that one, we can terminate the search and say we cannot find the key. But there's another type of blank entry in the table, which is an entry that had a value but was deleted. So we put the flag there that says that this is the case, so that when we are searching next time, we get to that, we say, yes, it is blank, but there was an element here, so I should not terminate the search. I can probably still find the element somewhere else. When we are doing insertion, when we come to such an entry that has that flag set that there was an element is deleted, we can just insert there. And this is how things will work. Now, one important property we want about this probe sequence. So if I look at HK0, HK1, all the way to H of K m minus 1, one important property about it is that we want the values of these to be a permutation of the values between m0 and m minus 1. Okay, so we would like for this to be permutation, right? We don't want this HK0 and HK1 and m minus 1 to be all 5, for example. That doesn't make any sense, right? So we want every probe sequence like this to be a permutation of the numbers between 0 and m minus 1, because that's how we, in the worst case, we end up looking at all elements in the hash table in search of that value. Now, what are these functions h of k0 and h of k1? How do we design them? I'm not gonna talk about this in details. You can look in your book, in the CLRS book. There are examples of linear probing, quadratic probing, double hashing. So there is linear, and there's an example of quadratic, and there is one example of double hashing. So these are all functions that map, again, from U cross the set from 0 to m minus 1 to the set of 0 m minus 1. And each one of these functions produces some of these so each one of these functions is going to produce a permutation for the probe sequence. But one important property when we want to analyze the running time of this hashing technique is whether all the permutations appear with equal probability, because that's very important, or in some sense a probability of 1 over m factorial, right? Because there are m factorial permutations, and do they all appear? So if we assume that we have such a function that generates all the permutations, uniformly, then we can now get good results on the running time of search and insertion and deletion using open addressing. In this case here, keep in mind that alpha is which is the load factor n over m, is smaller than 1, okay? Because we don't have linked list and entries here. So m, the number of slots in the table, has to be at least equal to the number of keys that have been mapped, right? So if we hashed 100 keys, n equal 100. If we hashed 100 keys to the table for sure has at least 100 entries, okay? So m is at least equal to n. Otherwise, we cannot insert things there. So if we have open addressing and we have uniform hashing, then in the worst case, and we are searching, the number of unsuccessful searches, okay, for a key. So unsuccessful as in k is not in the table, and we have to do a lot of work. In the worst case, this number is 1 over 1 minus alpha. Again, remember that alpha is smaller than 1, okay? So this is in the case of searches here. And again, I'm not going to go through the analysis itself. And we get similar results also in terms of insertion and deletion. And if we go into successful search, the running time then is, or not the running time, is that the expected number of lookups in that table or probes is 1 over alpha log of 1 over 1 minus alpha here, okay? And these two results are very important here because they tell us that open addressing would work very well. But again, keep in mind that m has to be large enough to be able to accommodate the n keys. That's not a serious problem, because even when we do collision resolution by chaining, we are still using a lot of space for the linked list themselves, okay? Here we don't use a linked list, but the space that the linked list do not use anymore, we can actually build a larger table. But again, an important thing is that this probe sequence, we would like it to be a permutation. That's easy actually to get it a permutation. What's not super easy is to generate this permutation uniformly at random. If we can generate them uniformly or close to uniformly, then this type of hashing works well. Okay, this is open addressing.